couple minutes for people to log in and attend. Hello, everyone, and welcome to our SubC TED Talk, not TED Talk, Tech Talk. We are just going to, again, give a couple minutes for people to get logged in, and then we will get started. We are really excited to have everyone here today. If throughout any of the talk today you have any questions, please put them in the chat. We will have time at the end of the call to go over your questions that might come up throughout the course of our tech talk today. We'll probably give people maybe another minute or so to log in to our talk. Again, welcome. We are going to be talking today about time-lapse programming to power management, solving the biggest challenges in underwater monitoring. And again, we'll maybe start in about 1 minute, and feel free to post your questions in the chat. Okay. We are nearly going to get started. Welcome to those who are just logging in. If you didn't hear what I said before and you're just new to logging in, just a reminder, if you have any questions, please post them in the chat. We will have time near the end of the tech talk for questions. And I think we're going to get started. So hello and welcome again to our tech talk from time-lapse programming to power management, solving the biggest challenges in underwater monitoring. We will be sending out a recording of this webinar after the fact as well. So you will see that and be able to revisit anything that you want more information on. My name is Marcy. I work at SubC Imaging, and I'm going to be your host for today. Before we get our talk started, I wanted to give you a quick overview of SubC Imaging in case you are not familiar with us. So we are based in Newfoundland, Canada, and for 15 years now, we've been helping companies with surveys and inspections. We are experts in both hardware and software and are trusted by more than 220 clients in over 30 countries, including top names in marine science and offshore energy. And these are just some of the companies and institutions that rely on us because our imaging solutions deliver consistent, high-quality results. Today, it's my absolute pleasure to introduce our two speakers who are experts in this topic. So first is Brent Lackey. He is the lead engineer behind SubC Imaging's most advanced technologies. He played a key role in developing our exclusive hibernation technology, which we're going to talk about today. He led the team designing our upgraded tow camera system and was a key member of the inaugural expedition to Antarctica in the hunt to capture footage of the colossal squid. The team used SubC Imaging's tow camera system in their mission. He also recently developed a Rayfin camera capable of reaching 11 kilometers in depth and spearheaded the initiative to make SubC Imaging lasers FDA compliant, making us the only company to offer this designation. Brent's going to be joined today by Adam Rowe. Adam is the co-owner and one of the first employees at SubC Imaging. He is the VP of software, and he has spent his career developing software apps for ocean-related professionals. He and his team focus on making cutting-edge systems with a really intuitive user experience. And his recent work includes working on adaptable remote operations technologies and the Rayfin camera software upgrades like the ones you're going to hear about today. So what are you going to hear about today? So today, what you can expect is we're going to sort of first set the stage on underwater monitoring, and then we're going to be focusing on four main challenges for underwater monitoring and their solutions. We're going to give you some real-world examples of the technology in action. And at the end, we are going to have a Q&A. So again, if you have any questions, please post them in the chat and we will get to those towards the end of the talk. And without any further ado, I'm going to hand it over to Brent to get things started.
Thank you, Marcy. We're going to start today by setting the stage and getting everyone on the same page about some of the terminology, ideas, and solutions that we're going to talk about. All right. What is underwater monitoring? Underwater monitoring is the process of collecting visual and environmental data to study marine life, track habitat changes, and inspect underwater structures. Some examples of battery deployed underwater monitoring are BRUV systems, Beta remote underwater video, and some long-term observatories. BRUV systems are typically for shorter deployments. They normally consist of a camera, battery, lights, and sometimes lasers for scaling, and any additional sensors that you might want to add. These are normally deployed with some bait to attract marine life, and deployment duration can be anywhere from overnight to several days. Battery-powered observatories are very similar, but tend to be aimed at long-term observations. These are generally more robust frames intended to weather extended deployments, located near interesting or unique marine life or underwater features. And typically the batteries will be much larger to achieve these deployments lasting anywhere from months to over a year. Recording is generally set up to be more incremental, meaning videos and photos are taken every so many days or every so many hours. So what is autonomous time lapse exactly? When we talk about being able to do things autonomously, we're referring to being able to write a script of actions or a list of actions for the camera to take. These actions, such as setting your lights to a certain intensity, turning your lasers on and off, taking a certain number of stills, adjusting your focus, your exposure values, recording video, stopping video, etc. Basically, it's a list of all the things you want the camera to do, all without your direct interaction that can run by itself autonomously. Adam will be demonstrating some examples later in this presentation that highlight the wide range of customizations that are possible in our script builder. Time lapse is referring to taking video or stills on an intermittent basis over time. For example, setting up an observatory near some interesting feature and observing it over the course of a year. In this case, recording continuously while on battery power is almost impossible. The power requirements just won't make sense. But recording some short snippets of video and photos every day over that entire year is completely possible and would provide you with an entire year worth of observations. And additionally, there's also nothing stopping the system from being able to record continuously, such as an abrupt deployment, where you just want to drop the system, see what happens continuously over the next 24 hours. In that kind of situation, you would still be able to avail yourself of all the customized features in our script building. The autonomous time-lapse system. This is the overall system that we have created that will address all the challenges we'll be talking about today and combine all the solutions into a single system. The system is designed for battery-powered autonomous deployments like the ones I just mentioned. The system centers around our Rayfin camera line, which are capable of time-lapse, performing scripting, and onboard recording. The software on our camera also allows it to switch to live viewing mode, giving you real-time access to the camera feed when needed. This flexibility lets you use the system both for long-term monitoring and on-demand observations without requiring additional hardware. To extend the capabilities of our standard system, we have also developed the Rayfin Hibernation Time-Lapse Camera variant. So in addition to onboard recording and scripting, it also allows us to cut power to attach devices and to enter long-term sleep mode. Why is that important? Well, it allows us to only power specific equipment when needed and keep it turned off otherwise. And with our low power sleep mode, which in this case we call hibernate, we cut our power consumed by over 900 times. So it consumes 900 times less power when sleeping than when it's idling. We're now going to talk about the challenges faced in underwater monitoring and some of the solutions we have developed to combat them. One of the biggest challenges in battery-operated systems is the limited deployment duration and power constraints. Battery-powered deployments can range in duration from days to more than a year, but power efficiency is key. Deep-sea batteries can be costly and are a significant limitation in how long a system can run, meaning you want to ensure you squeeze out every last drop of power that you can. You want all of that power that's being used in progressing your mission, in powering the lights for illumination, powering your lasers for scaling, powering your camera to take images and video. On these longer deployments, you'll have losses from everything connected to the battery. Your lights, your lasers, your camera, they'll all draw small amounts of power when connected, even if they're not doing anything. That power draw, even when the system's just idling, starts to add up significantly over time. To combat these losses over time, we've developed a low power sleep mode for the Rayfin Hibernate. This hibernation mode cuts power to all attached devices, so no power can be lost to any auxiliary devices. It also puts the camera into an extreme power saving mode, waking up on an interval which is set by the user. So if we want the camera, for example, to wake up once every 24 hours and it runs a 2-minute script, it will do that, and then it goes back to sleep for the other 23 hours and 58 minutes. And by going to sleep, we're only consuming 1/900th of the power that the camera would have consumed if just left idling. So now that you know what hibernation is, what does this look like in real terms? Let's take a look at 2 different scenarios. One is going to be a 1-week-long deployment for a BRUV system, and the second one is going to be a 1-year-long observatory deployment. Let's take a look at the short-term deployment first. In this scenario, we're going to have 2 LEDs set to 50% intensity, and the laser will be on during each cycle. We'll record video for 1 minute and take 10 digital stills. During each of those stills, it's going to flash the LEDs, and it's going to do this once every hour on the hour for 7 days. This means that the camera will operate in cycles and do its thing for about 2 minutes roughly, and then do nothing essentially for 58 minutes, then repeat that cycle. So in this first plot, you can see the power consumption of the entire system using our standard Rayfin camera over the course of 7 days. The blue part is how much energy is being spent on running the script. This is the energy to run the lights, take the photos, record the video, and power the lasers. The orange part is how much energy the system uses just to stay on during those 58 minutes between the 2 minutes of activity. As you can see, the system uses more power to wait out those 58 minutes between uses than it does in actually capturing data. In this case, about 15.3% goes towards data collection, almost 85% goes to waste. In the second plot, we're showing the exact same setup, exact same scenario, but this one uses our hibernation camera. You can see that we've gone from about 15% energy use towards data collection all the way up to over 99% with the hibernation variant. We only have about 0.6% of the energy being wasted waiting between cycles. This chart shows you in absolute terms how much power is being used over the deployment period. The hibernation camera draws almost nothing while sleeping. The power that is used is therefore used in capturing data. And you see that in this chart where with the hibernate, which is the orange line, and the standard system, which is the blue line, hibernation uses about 6.5 times less power than the standard unit. So in this scenario, the standard unit would run for 1 week, consuming about 1,200 watt hours of power, whereas hibernate, if it used the same amount of power, could run for 6.5 weeks. Now, you might ask, okay, well, what happens if I run the system continuously with no waiting between recording sessions? Well, as the wait period becomes smaller and smaller, you'll waste less and less power waiting between cycles because your wait period is getting smaller. If you eliminate the wait completely and you don't have cycles, you just record continuously, then there's no difference between the hibernation unit and the standard unit. But I chose this example because the benefit of the hibernation system when attempting to do a time lapse, even with such a rapid cycle of once every hour, still results in dramatic energy savings. And it lets you leverage your existing batteries as much as possible. All right, on to our long-term observatory example. So we're going to keep the exact same scenario as before. We've got 2 LEDs set to 50%. Lasers will be on. We'll record a 1-minute video, take 10 stills with strobing. And we're going to do this once every 12 hours instead of 1 hour. So every 12 hours, and we're going to do it for 365 days. So a full year. And once again, this means the camera will operate in cycles. So it'll do its thing for about 2 minutes, then do nothing for the following 11 minutes, 58 minutes, or 11 hours and 58 minutes, then repeat. In the first plot, you can see a similar result to short-term deployment example. The blue part is how much energy is being spent on running the script. The orange part is how much energy the system uses just to stay on between cycles. So in this case, you can see we're worse off than we were before. About 1.4% goes towards data collection, whereas the remainder all goes towards waste. This is obviously not good and wastes a huge amount of power. In the second plot, once again, we're showing similar, we're showing the same scenario, but this is our hibernation camera. And you can see that we've gone from 1.4% of the energy being used for data collection all the way up to 90, almost 93 with the hibernation variant. We only have about 7% of the energy being wasted waiting between cycles. This chart, very, very similar to the last one, shows you in absolute terms how much power is being used over the deployment period. So this one is showing us a full year in days with power consumed on the side. The difference is far more pronounced between the standard unit and hibernation unit when our deployment length increases. The power used by the standard system is over 56,000 watt hours, whereas the hibernation unit consumes only about 860. The hibernation unit in total uses almost 66 times less energy to do the exact same thing. And 56,000 watt hours is utterly impractical. You would need a massive power bank to achieve that, and the expense would be substantial. 863 watt hours, though, that's pretty easily attainable with current off-the-shelf battery solutions, and you might have some of your own that could accomplish that. So to that end, we are available to help with battery options for various deployment durations and can fit a solution to your needs. This system is compatible with most third-party battery sources, so no need to buy special batteries, and you can use what you already have.
So another challenge that we find clients are often facing with underwater monitoring is data management. So over these long-term deployments, like Brent was saying, you typically collect a lot of data. This could be videos, stills, and any instrumentation data that would be logged as a CSV. And depending on the nature of your system, these could all be going to different locations and different places. But with the Rayfin, that truly acts as an underwater hub where we're able to save all of that data and media in one place. So what would traditionally happen is you would take all of your data, save that to a CSV. You would have all of your images that will be recorded typically to a directory, and these would be disconnected. So after you retrieve all of the data and media, you would then typically need to write some sort of application to be able to go and read your CSV file, go through your folder of images, and then try to create a link based on time to the areas of interest based on your data and on your images. So what we've done is we're able to take all of our instrumentation data and embed that as EXIF information into each still as it's acquired. We still have a CSV log for any additional use, for any additional information that goes in there, but all of your location data, your depth, that is all saved in real time on each still. So we're able to leverage our directory and file name templates to make sure that we have all of our timing accurate. We also have a number of streamlined data transfer methods to be able to retrieve all of that footage afterwards. We've got a web-based downloading method as well as a method that leverages Samba So we should have an option that will work for your environment to get all of that to your PC. And with the ability to log all of that data into each individual still, we can use that in a lot of third-party applications to be able to show where all that data was collected. So we have a partner in Beagle, and we're able to upload all of our project information and our data set to Beagle, and that'll plot on a map and allow for global annotations. But you could also just see in a regular online EXIF viewer, when you bring in a still, you can actually see the plot of where that still was taken on the map. We have several clients who are able to utilize this, and we've got feedback that they're able to save up to 50% of their post-processing time, which obviously accounts for a lot of savings and is extremely significant.
Our third major challenge is biofouling and image clarity. Depending on your deployment depth and environment, biofouling can be a significant issue, especially on those longer deployments. Marine growth and particulate deposits on your camera lens can reduce image quality. On your sensors, it'll reduce sensor data over time, leading to obscuring your target, loss in resolving power, loss of measurement accuracy, and even loss in light if your LEDs become covered in growth. Even in short deployments, you can still see significant buildup of debris in a more turbulent environment. And in deployments approaching a year, your equipment can be completely obscured, and totally negating any expense spent on larger batteries to extend your deployment duration. How do we overcome this? One of the best ways to mitigate biofouling is very simply to mechanically remove it. For deployments down to 200 meters, a mechanical wiper can be installed on our Rayfin camera to wipe the lens at a set time interval. This wiper is completely self-contained with its own battery source and is capable of operating for up to 1 year deployments. It's been proven to effectively remove biofouling and debris deposits on the lenses. By being able to consistently and repeatedly physically clean the camera lens, it prevents biofouling from building up and allows for those extended deployments, especially in shallow water, to be viable without needing frequent visits to clean the system. This wiper can also be installed on any sensors you might have or our underwater LEDs. For systems that need to go below 200 meters, so there's a UV light option, which has been proven to mitigate biofouling. It's a bit more power intensive than the wiper option, but could be a great fit for those who still need something rated deeper and depending on your water conditions and environment. Here is a short video showing the wiper in action on a Rayfin camera. This is located down on our observatory platform at our local marina located in Clarenville, Newfoundland, Canada. Terribly exciting, I know, but this can mean the difference between getting clear imaging results over your entire deployment or just wasting half of your deployment because the lens gets dirty midway through and now you can't see anything.
So the fourth and final challenge that we often find with underwater monitoring is the programming complexity. As you can imagine, there's a lot of pieces of technology at play here. And what it would typically mean would be that you would need someone with programming or coding experience to be part of your team. And they would have to likely interact with a number of APIs from all the different manufacturers to be able to control this equipment long term. This can be, significantly challenging in ensuring that you get a deliverable result, as the complexity of interfacing all that would be high, and the reliability can be a bit suspect. So, in order to solve and overcome this challenge, we've developed a user configurable interface. It's a drag and drop interface based off of block coding. And this really helps streamline the setup, and you can do all of your complex operation and control any auxiliary devices from our visual script builder. We also have access to the camera's full API, so we're able to control all of the different settings, including the exposure, focus, white balance, to make sure that you're always able to get the optimal images. So I'll run through a brief demonstration of how this can be configured and set up. So this application runs on the Rayfin itself. It opens up in a web browser, and what we're seeing here is the actual work area, the workspace of the visual script builder. Over on our left, we have all of the different functions and commands that are available to us, as well as all the different properties that can be evaluated. We're also able to fire off events when certain triggers are met. These are all grouped and categorized together that have like functions. And then we also have a color coding system as a rule of thumb for features and functions that have a similarity. For example, red are for executing some process like starting recording or starting RDI, yellow typically for setting some values. And they also fit together like puzzle pieces. So incompatible blocks don't work together and they actually snap in. So you can build a bit more confidence in knowing that your script is going to execute properly when you click the play button. Up in the top left, we've got your standard interface, user interface controls for saving, loading. We can run our script from there. We also have the ability to upload and download any scripts that you might have from colleagues or from SubC if you get stuck and you want help. We're always available to help with clients who might be running into some trouble with building their scripts. And down in the lower right-hand corner, we've got our workspace controls. And this helps us navigate the workspace as we're building our scripts. We're able to clear, zoom in and out, and then center on the actual blocks that we've dragged in. So we do have a couple of tips for creating what we would consider a good script. Given that these are run autonomously, we want to make sure that we're always kind of setting back to some default standard to make sure that we're always in the same starting point. So we want to first make sure we adjust all of our exposure and lens controls, make sure we have our focusing right for the environment that we're working in and our lighting conditions. And that will ensure that when we do take an image or we do take video, that the conditions are right from the camera's perspective. After, we like to configure our quality settings. This could be the quality of the video or of the stills. Also, we can set all of our file names and make sure that they're always set to a consistent value so that over time things aren't changing or drifting. And then after that, we perform the actual execution functions of our script. So this is where we might run through some loop and perform some functions repeatedly, or we could just start recording, start our rapid digital imaging process, and then this will actually do the acquisition part of our script. So I'll run through an example here of what could be used for a BRUV deployment. BRUVs typically are between a week or a day, and we'll have them run and collect a series of footage throughout that time period. So first off, we're going to adjust our exposure and lens, and we're going to just set our exposure to manual, set our ISO and shutter. Each of these are blocks that we would have dragged in and connected together individually. Then we're going to configure all of our quality settings. So you can see it's very readable. It helps if you have a bit of programming or coding experience, but even if you don't, we have a lot of templates available as well that you can kind of look through. We tried to make it lower the barrier of entry as much as we could by making it as simple to read as possible. So you can see we're setting our image format to JPEG. We're setting our recording preset to full HD at 30 frames per second. And this is where we're doing all the file and quality setup of that video and of the video and stills. Now we're into the execution portion, and this is where things get maybe a little more complicated. But if we break it down, we can see we're just going to turn on our strobe brightness of our LEDs. We've got a repeat indefinitely loop. So what this is going to do is as soon as you apply power and the camera boots up, it will run this until power is taken away. So we're going to turn our lamps on and we're going to start recording. We've got our wait, and that means we're just going to sit and record for that period of time. And then we're going to stop our recording. We're going to turn our lamps off so we can get full power on our strobes as we're doing our rapid digital imaging, which is taking a series of images up to a rate of 2 Hertz. We're going to do that now for a period of time until we stop. And then we're going to wait until we repeat and do everything inside that loop all again. So here's what that looks like all together. We also have the ability to add comments in here and help you organize what it is you're doing. These can be very simple and range to very complex depending on what it is you want to do. There are a lot of features in here. We've got full documentation available. We also have a more in-depth demo of walking through it that you can get from us at team@subcimaging.com, where you can contact our sales. So what can we do now after we acquire all this data? One thing that we have a lot of clients doing is making a time-lapse video of all of the images that they acquire, or a subset of images that they acquire. And then you can really get a good visualization of that long-term change in a fairly short and concise video. We have instructions available on how you can do this yourselves with free-to-use software. And again, that can all be acquired through our contacting our sales team at team@subcimaging.com.
Thank you so much, Adam and Brent. That was amazing. Some really great information there. Before we get into the Q&A, I just wanted to show some real-world examples of how this technology is actually being used by different institutions and organizations. So the first thing I'm going to show you here is a snippet of time-lapse footage. And this comes from the National Science Foundation's Oceans Observatories Initiative Regional Cabled Array, which is maintained by the University of Washington. Hopefully that'll get started here in just a second. But since 2014, their Southern Hydrate Ridge camera has been continuously monitoring a methane seep site in the Northeast Pacific at a depth of approximately 780 meters off the coast of Newport, Oregon. It looks like we're having a bit of trouble with the time lapse, so I'm going to see if I can get that going. Just a little bit of information there is that they used the SubC autonomous time lapse camera, and researchers were able to capture a full year's worth of images from August 27th, 2023 to August 27th, 2024. And that provided them with a long-term view of methane seep activity. This site experiences seafloor changes, including methane hydrate formation, explosive venting events, and interactions with deep sea ecosystems. We are still having a bit of an issue here. Let's see if we can, we'll give it one more try here. There we go. It's still a little choppy. I think that we're having a bit of an internet issue here. But we will be sending out the recording, and we can send out a link to this video as well. One other thing to mention is thanks to their open access data, researchers and students and educators at the University of Washington and beyond are able to study these methane seeps in greater detail. So again, looks like we're having a little bit of internet getting that video to play for us live. Apologies for that, but we will send out a link to that video for you to look at because the time lapse is actually very impressive, and we'll send that out. Last try here. We'll see. Starting, you guys are just seeing the little first bit of it. So again, we'll send out that link. The next sort of real world example of people who are actually using the system right now in action is the University of Western Australia. So their researchers needed a way to monitor deep sea biodiversity over an 18-month period in marine parks in Australia at depths exceeding 5,000 meters. So they needed that solution that can maintain long-term power, prevent biofouling, and ensure that high-quality imaging in extreme deep sea conditions. So they use our SubC autonomous time-lapse system with that optional hibernation mode that Brent really spoke about. They also integrated environmental sensors so they could get that valuable context data for their research. And the results were that over an 18-month period, they were able to capture high-resolution time-lapse images every 12 hours. They were able to get new insights into benthic activity, marine snow dynamics, and species distribution. And again, it allowed that continuous monitoring with minimal intervention. And Dr. Todd Bond from the University of Western Australia, let us know that being able to capture high quality data in the deep sea over long periods wouldn't have been possible without this unique hardware and software. It's the only off-the-shelf system I've come across that combines very high-quality time-lapse imaging with a hibernation mode, which is exactly what we needed to monitor Australia's deep sea. It's made a huge difference in how we study these ecosystems through time, and it's given us insights we couldn't have gotten any other way, which is fantastic feedback from Dr. Bond. The final sort of real-world example that we'll give you comes to us from Fisheries and Oceans Canada. Researchers were looking at long-term monitoring of fish populations and habitat changes. And again, they were also looking for a solution that provided that high-quality long-term data collection while managing power consumption. And the SubC autonomous time-lapse system was their answer. The system allowed researchers to collect the data they needed for fisheries research, and the results included detailed visual data on fish behavior, habitat conditions, and long-term environmental trends. And, where are we here? This is an example. Again, we're having a little bit of issues with the internet to get that video. You can kind of start to see it there with the footage they were able to capture. Again, we'll send some links to these videos for you to be able to watch without this delay. So, we've just spent, about 40 minutes now talking about some of the key issues in underwater monitoring. So I just wanted to, before we get to the Q&A, just do a little bit of a wrap up of some of the key takeaways. So the first, again, was power management. So we covered how the optional hibernation mode drastically reduces power consumption. Those pie charts that Brent showed were really could really show you the difference in handling extended deployments without adding more batteries. The second thing we looked at was data handling. So organizing and transferring large data sets, embedding the metadata in there, and using a structured workflow to streamline post-mission analysis. We then looked at some biofouling prevention methods, so solutions like wipers for shallow water and UV technology for deep water. And then finally, scripting and automation. So how the visual script builder simplifies programming and makes it easier to schedule recordings, even if you don't have a lot of programming experience. You can customize your settings and really automate the operations without that complex coding. So if you do want any more information on any of the technology we talked about today, you can email team@subcimaging.com. And now we're going to get into a little bit of a Q&A. So if anyone has any questions, please post them in the chat. You can do that now. To get us started, was wondering, Brent and Adam, if you can talk a little bit about some of the most common mistakes people make when setting up a script and how you can maybe avoid them.
Yeah, so I think one of the most common mistakes that we sometimes see is our clients are not necessarily giving the system a long enough test for bench testing when they receive it. Make sure that their scripts are working and that they have real world data to support any calculations for battery durations. It's absolutely critical to make sure you can spend as much time as possible making sure beforehand that everything is going to work smoothly, so that when you come back, you get what you expect, and when you retrieve the system, that you get the footage that you expect, and there wasn't some glitch or error that could have been accounted for and throw everything off.
That's awesome to hear. And I think one of the other things is a lot of people don't realize that SubC provides free onboarding. So when we, if you get a SubC imaging camera or system, in addition to the bench testing that you should be doing on your own, we do offer onboarding to help you get set up. We have a couple questions from David. The first is, could in-situ power generation be added, such as tidal generation, to extend a camera deployment battery life?
Certainly, we don't personally have a solution for that. But if you did have something that was able to recharge your battery, then that's going to increase the camera time. And by optimizing the power draw of the camera and attached peripheral devices like your LEDs and lasers, you can really leverage any power generation that you might have.
Fantastic. Thank you. David also asks, are you using machine learning image detection segmentation techniques to filter image captures which contain defined points of interest?
So we haven't done too much with that. We have in the past gotten into it a little bit, but we're still waiting for that kind of perfect development partner to really help define a really good business and use case for that. Of course, that doesn't mean our images can't be used for that. Once acquired, they could absolutely be fed into any ML or AI kind of engine to be able to train to get any of the results that you're looking for. It's just not something we offer as part of a baked-in solution.
Thank you. Another thing I'm curious about, and the audience might be curious about as well, is we talked a little bit about how this camera is for, does the internal recording, but it actually can also be used for live deployments as well. Can one of you talk a little bit more about that functionality?
Brent, you want to go ahead and take that one?
Certainly. So while our camera can be used in an autonomous fashion, so hooked up to a battery and deployed as a standalone unit, for instance, just sent down with a rope. So you've got all your equipment on a frame with a battery, you send it down with a rope, you have no connection to the top side. We can run that camera autonomously. Another situation, which the exact same camera can be used for, is attached to an ROV system. With live video recording and digital stills sent back topside simultaneously. All recording in that case is done on the computer that you are using. So in that case, we're not using onboard recording. We're sending it all live back to the surface so that there's no lengthy download period. Once your mission is over, everything is on the computer that you are using for the deployment. And everything is available at your fingertips. So there's no post-mission downloading or anything like that. Everything is available in real time. You can have somebody taking a look through the photos that have been taken while somebody else is operating the vehicle. That can all be done simultaneously and live.
That's awesome. Two-in-one camera. Mm-hmm. Again, if anyone has any questions, please post in the chat. The final thing I was wanting to know as well is around how does the system handle extreme conditions like deep sea pressure, temperature changes, and what are the different depths that this system can go to?
Well, our standard unit is rated for 6,000 meters. It's made out of titanium. We use sapphire glass for our windows. So it's all rated for full ocean depth, 6,000 meters. Great in lower high temperatures in most extreme environmental conditions. One extra thing I did just want to add was if you were interested in, for example, monitoring species during day-night cycles, that is completely doable with our autonomous hibernation system. We have set it up so that if you were recording every 12 hours on the hour, it really is on the hour. So if your script is 5 minutes or 10 minutes long or 20 minutes long, no matter what it is, it's always going to start up at the exact same time. So if we set it up for 6 hours, for instance, say it starts at noon, it's going to turn on at 6, it's going to go to midnight, it's going to go to 6 in the morning, it's going to go to noon. And it's going to be accurate over a long course. We have very minimal drift on our internal clock. So if day-night cycles were something that you were interested in and it was very important that it turn on at the same time every day, that is entirely doable with our system.
Thanks, Brent. Again, a final call for questions and answers. If we don't get any, that's okay. If you have questions that you want to follow up directly with our team, again, email team@subcimaging.com. Everyone should be getting a recording of this webinar tech talk in no more than a day or so. And we'll also be sure to follow up with the links to some of those videos so you can see that time lapse in action. Apologies that didn't work. Sometimes the internet does not cooperate when you're doing a tech talk. Again, thank you so much to everyone for registering and coming out. And we're really just excited to share the different ways that we can help solve your biggest problems and challenges when it comes to underwater monitoring. That's it for now. Thank you so much. And we'll hopefully see you at another webinar soon.
Thank you. See you.
Bye.
Thank you. See ya.